Hello everyone, my name is Dr. Subhasis Das. I am working as an associate professor in the Department of Electronics and Communication Engineering, SR University, Warangal, India. This is my YouTube channel. Please do like, share, and subscribe my channel. Today we will discuss about the half-wave rectifier. Okay. So the topics in this video will cover are PN junction diode as rectifier, then basics of a rectifier, then half-wave rectifier, and then we will discuss some of the disadvantages of half-wave rectifier. Okay, so let's start. First thing we need to understand why we need a rectifier. Okay, first we will see few points. What are the components? Why we need this? So, a PN junction diode is a two-terminal device that is polarity sensitive. That means here in this image you can see that this is the PN junction diode, right? So this is the PN junction diode, and as you know, this is the P side and this is the N side. What is the purpose of this PN junction diode? To change your signal from AC to DC. Later we will see that while changing from AC to DC, actually the diode is making it a pulsating DC, not exact DC. Because in the case of DC, we generally think that the voltage level will be constant throughout the time period. Okay, but in the case of rectification, we will see that it is actually pulsating DC. Okay, we will see those things later. Okay, let's first understand the different properties of PN junction diode. Okay, so in forward biased condition, the diode conducts and allows current to flow through it without any resistance, that is the diode is on. Okay, so here the diode is working as a on switch. What is the condition for that? The forward bias. Okay, then you might ask what will happen for the reverse bias. Well, in the reverse bias condition, the diode does not conduct, okay, and no current flows through it. That is, the diode is off or providing a blocking function. That is, if you consider a switch, then the switch is in the off condition for the case of reverse bias. Okay, so basically your diode can be acting as a switch either in on or off condition, right? Thus, an ideal diode acts as a switch, either open or closed, depending on the polarity of the voltage placed across. Okay, so maybe you are already aware that if we connect a power supply, that is P side is positive and N side is negative, then we will call this as the forward bias. And when if we connect a battery negative to the P side and positive to the N side, then that condition will be called the reverse bias condition. Okay, so this is how we can use a PN junction diode as a switch. Okay, now we will try to see what are the basics of rectifier. Okay, so rectifier is defined as an electronic device or rather circuit used for converting AC voltage into unidirectional voltage, that is normally we say DC voltage, right? So here in the image you can see that if we give a line voltage, that is 230 volt at 50 hertz, that is a line voltage AC we see in our uh, any applications. Okay, and the diode is making it DC, which is constant voltage. Okay, so if we see the DC curve, ideally it should go like very much straight. Okay, if this is your signal, this is voltage and this is T. For the DC it should go like this, whereas for the AC it will be going like this if it is sinusoidal. Okay, so this is the difference, that we will make that at a constant voltage, right? So this rectifier utilizes unidirectional conduction devices like a vacuum diode or p-n junction diode. Okay, so in that case, what we will see that these rectifiers can be categorized into two, that is half wave rectifier and full wave rectifier. Okay, so now we will see the what is half wave rectifier and what is full wave rectifier. Okay. Okay. So now we will see what is half wave rectifier. So it converts an AC voltage into a pulsating DC voltage using only one half of the applied AC voltage. Okay. If you see the image right hand side below, you will see that the top portion is showing a sinusoidal wave, that means full wave. Okay, with a positive half and a negative half. Now, in the case of half wave rectifier, it only conducts one of the half. Okay, either the positive halves were converted into DC or the negative halves were converted into DC. It cannot convert both the halves. Okay, so that means we can see that if we want to convert the both the halves, then this will not be useful. We will come to the disadvantages in the later part of this video. Okay. So what we'll see that the rectifying diode conducts during one half of the AC cycle. Okay, let's before going to analyze the uh, graph, we'll first see the circuit diagram. Okay, so here as you can see, this is the AC input voltage, right? This is the AC input voltage and this is the transformer. Okay, okay, so this transformer what is doing, it is just stepping down the voltage. Okay, because your diode cannot withstand this many much of voltage, because this is 230 volt, right? That means the transformer will just convert, no, it will not convert, it will just stepping down the voltage. Okay, and here at this point diode is connected, right? So at this point diode is connected. So at this point and this point it is sinusoidal, right? But when it passes to the diode, it is being converted, right? So we will see, try to understand the operation through this graph. Okay. Now see, when the positive half of the AC signal comes, let's say this one, when the positive half comes, because this positive side is connected to the P side. Okay, this is the P side and this is the N side, right? So when the P side is connected with the positive, then the diode is in forward bias condition. So it is conducting and it is working like on switch. Okay, so that is why at this hub we are getting as per the waveform. Okay, output of that diode. But when the next hub comes, this side becomes positive, right? So this side becomes positive. and then the condition becomes that this positive side is connected to the n-type, and because of that the diode becomes reverse biased and it is acting like a off switch. That means it is not at all conducting. So we will not see any voltage here. It will be showing like 0 going like this. And when the next half comes, then again it will working like this. Okay. So that means it will only rectifying half of the cycle of that sinusoidal input AC signal. Okay. Now we will try to understand more details. Okay. Let Vi be the voltage to the primary of the transformer. What is primary of the transformer? So as you know, the transformer has two coils, and actually depending upon the turn ratio of that two coils, we will see the step down or step up performance of the transformer. So the input side where the input AC signal comes is called the primary side, okay, or the primary coil, and the output side from where we are taking the output voltage from the transformer is called the secondary side, and depending upon this turn ratio of primary and secondary, how much voltage output will be decided. Okay. So here we are predicting that our AC signal is Vi is equal to Vm sin omega t, because we are considering a sinusoidal wave. So Vm is the maximum voltage and omega is the angular frequency and t is time. And here we are saying that Vm very greater than Vy. What is Vy? So Vy is the cut-in voltage of the diode. Okay. So the basic condition of the sinusoidal wave is that the maximum voltage or the peak voltage should be very greater than the cut-in voltage of the diode. Otherwise, in the positive half also for some portions it may not be turned on. So that is the reason why we want to make the peak to peak voltage very high. Okay. So during the positive half cycle of the input signal, anode of the diode becomes more positive with respect to the cathode, that is the P side and N side. So the diode deconducts. So here anode stands for the P side and cathode stands for the N side. So the diode deconducts in this case. And for an ideal diode, the forward voltage drop is 0. That means that is a perfectly on switch. Okay. The whole input voltage will appear across the load resistance RL. Here you can see it will appear across this load resistance RL. Okay. During the negative half cycle of the input signal, what happens? The anode of the diode becomes negative with respect to the cathode. That is, your P side becomes more negative compared to your N side. Okay, that means the diode D does not conduct, right? For an ideal diode, the impedance offered by the diode is infinite. Basically, it is working like an open switch. Okay, the whole input voltage appears across diode D, hence the voltage drop across RL is 0. Okay, because as you can easily see, okay, forget about all these terminologies. If it is like a open switch, nothing is passing through. So that means here we will not see any voltage. Okay, basically that it will be flat or zero. Okay, now we will see some parameters. So this is the basic working principle we have noticed or discussed. Now we will see different parameters to understand the quantitative nature of the half-wave rectifier. Okay, so first and the most important factor is the ripple factor. It is denoted by tau. So the ratio of RMS value of AC components to the DC components in the output. Okay, basically this definition actually shows like a mathematical definition, but if you want to understand physically, to understand physically about the ripple factor, we can easily say that the amount of AC component still available in the DC output from the rectifier is termed as the ripple factor. And to find the value of this, we make the ratio, like the value of AC components to the DC components. Okay, so here we go for this tau is defined as the ratio of RMS value of AC component divided by DC value of component, that is VRMS by VDC. This is very important formula to remember. And as you know that VRMS is equal to root over VRMS square minus VDC square. Okay, this condition also we already know. Now the tau becomes root over VRMS by VDC square minus 1. Okay, because we will just put this value here, and because of this the equation becomes, the final equation for the ripple factor becomes like this. Okay, this is one parameter. Now we know VDC is the average or the DC component of the voltage across the load and is given by VDC is equal to 1 over twice pi. In the bracket we will see the integration. Okay, integration of what? Vm sin omega t d omega t, and the integration limit is 0 to pi. Okay, plus pi to 2 pi 0 d omega. And finally, after getting the integration result, we will see that this VDC value becomes Vm by pi. Okay, so this is also a formula to remember always. Okay, so our IDC becomes VDC divided by Rm. That is very straightforward, Ohm's law, right? So once we put the value, the VDC value Vm by pi and the Rm, it becomes Im by pi, right? So it becomes Im by pi. Okay, so these are the two values we found, VDC and IDC. Okay, and from the VRMS formula also we will see the simplification. So VRMS is equal to also 1 over 2 pi 0 to pi, and the square of the signal all to the power half, that is equals to Vm is equals to, sorry, that is equals to Vm by pi. So ultimately we see that VRMS becomes Vm by pi. Now we will put all these values into the tau formula. Okay, because we already know the tau formula is equal to VRMS square divided by VDC square minus 1. So we will put this value Vm by 2 and the previous value of VDC, that is Vm by pi, into this equation. Okay, into these equations if we put, we will see that the value becomes 1.21. So, and this value is theoretical value. Any half wave rectifier we design, the value of the ripple factor will be 1.21. That is for sure. So the amount of AC present in the output is 121% of the DC factor. That means more than DC. So the half wave rectifier is not practically useful in converting AC into DC. As we already proved that it is not that much useful. That is, it is more than 100% of AC available in the output DC. So we cannot really say that is uh, a DC at all or not. Okay. Now we will see another parameter. Okay, efficiency. So the ratio of DC output power to AC input power. This is very simple to understand the parameter, because for any kind of efficiency you always compare the output divided by input, that this much of input we are giving and that much of output we are getting. So we can easily say that, okay, for getting that much of output, how much of input is required. So that gives us the efficiency. If the efficiency is 100%, means the output and input are same. Okay. So here also, for the case of half wave rectifier also, we will see the efficiency. Okay, here efficiency eta is defined as the DC output power divided by AC input power. That means PDC divided by PAC. Okay, you can see easily here. Okay, PDC divided by PAC. Right? Now we will put all the values. Okay, PDC means VDC by RL. Okay, so VDC square by RL. So because PDC will be IDC and VDC. Okay, VDC is VDC, but IDC is also VDC by RL and VDC. So that makes the equation VDC square by RL. Whereas PAC also similarly VRMS. So PAC will become IRMS VRMS is equal to VRMS square by R. Okay, that's what we have already replaced in this equation. After getting all the solution, you can see the value here 0.406, that is 40.6%. So basically, if you see that around 40% of the input power is converted into output power. That means if we want to consider or characterize this half wave rectifier as far as the efficiency is concerned, we will see this is not at all efficient. Okay, so the half wave rectifier efficiency is 40.6. Okay, now the next parameter is peak inverse voltage, PIV, the maximum reverse voltage that a diode can withstand without destroying the junction is the peak inverse voltage across a diode with the peak negative half cycle. For half wave rectifier, PIV is Vm. Okay, for half wave rectifier, PIV is equal to Vm. You can see it is written here. So that is peak inverse voltage will be the peak to peak voltage, maximum voltage of the input signal. Okay. Now another parameter is transformer utilization factor, TUA. Okay, the rating of the transformer in any power supply is called the TUA, and it is defined as the DC power delivered to the load divided by AC rating of the transformer secondary. Okay, if you want to put it mathematically, we can write as that PDC, that is the DC power delivered to the load, divided by PAC rated. Okay, the rated voltage of the transformer secondary is Vm by 2. Okay, as you can see here, it is Vm by root 2. Sorry, it is Vm by root 2. Okay, so the actual RMS current flowing through the winding is only Im by 2, right? So if you want to calculate TUA, so it will become PDC becomes Im by pi square into Rm, and your PC rated, this one becomes Vm by root 2 into Im by 2. And finally, when we are doing the final solution, it becomes 2 root 2 divided by pi square, that will ultimately give us the factor 0.287. Okay, that is the transformer utilization factor. What is form factor? Form factor is defined as the RMS value of the output voltage divided by average value of the output voltage, and as per the equation is concerned, it becomes 1.57. Okay, and what is peak factor? Peak factor is defined as the ratio of peak value of the output voltage divided by RMS value of the output voltage. That is Vm divided by Vm by 2, which becomes 2. So these are the values. 1.57, this is 2. These values are fixed. If you give the input different Vm also, that also does not make any change in this value. These are fixed. Okay, because as you can see, these are independent of any Vm or any other flexible parameter. These values are fixed only for the case of half wave rectifier. Okay, so now we will see what are the disadvantages of half wave rectifier. Elaborate filtering required to produce steady DC, that is V out, F out is equal to F steady DC. Okay, because this does not convert all the ups, that is very much uh, undesirable. Okay, the pulsating output voltage at the load contains alternating components whose basis basic frequency is equal to the supply frequency. Okay, so the rectified output is low. Output power is delivered only half the time. Therefore, output is also low. So you understood. These are some major disadvantages of half-wave rectifier. Okay. Now we will see what are some suggested questions from this portion. Well, the first question could be, what is a rectifier? The next one would be, show us how a PN junction diode works as a rectifier. So that means basically the working principle of a half-wave rectifier. Define the following terms: ripple factor, peak inverse voltage, and efficiency for half-wave rectifier. So all these factors, not only definitions, you should always remember the values also, because sometimes in the uh, numerical problems it may ask you directly that what is the ripple factor, or for that solution of that problem you might need to just write the value in some equation to get it more simplified. Okay, so be always prepare with the actual value also, because these are independent of Vm or some other parameters. Kind of these are already fixed values. Okay, so you should be better remember. Okay, then next is the draw the circuit of a half-wave rectifier and explain its operation. Okay, so basically this question number 4 and 2 are kind of similar explanation of the working principle of the half-wave rectifier circuit. Okay, the next question could be, a voltage of 200 cos omega t is applied to half-wave rectifier with a resistance of 5 kilo ohm. Okay, so here what is happening, 200 cos omega t. Okay, so this is the voltage input signal applied to half-wave rectifier with load resistance of 5 kilo ohm. Find the maximum DC current component, RMS current, ripple factor, and the rectifier efficiency. So these could be the questions from this section. Okay. Now we will just quickly remember whatever we learned from this lecture. The first point is that a PN junction diode is a two-terminal device that is polarity sensitive. We already noticed that if we change the polarity, the biasing condition will be changed, and hence the device action will also be changed. Okay, that means the polarity is very sensitive. Rectifier is defined as an electronic device used for converting AC voltage into unidirectional voltage. Okay. The rectifiers are classified depending upon the period of conduction as the half wave rectifier and the full wave rectifier. Okay. And when it comes to the half wave rectifier, we need to remember certain parameters of that. That is, the half wave rectifier converts an AC voltage into a pulsating DC voltage using only one half of the applied AC voltage. Okay. So we'll just remember those values. The maximum efficiency is 40.6%. VDC no load is equal to Vm by pi. Average current of the diode is IDC. Ripple factor is 1.21. Peak inverse voltage is Vm and output frequency is AF. Okay. So I hope all the listeners have understood and have that rectifier working principle and mechanism, and hope that you all understood this concept of halfway rectification. Thank you for watching the video. We'll see in the next video. Okay. Thank you.